Hello, I am Abhinav Sharma. Welcome to Python Wife. Let us learn about BigO notation and analysis of algorithm. There are multiple ways to solve a problem using a computer program. For instance, there are several ways to sort items in an array. You can use merge sort, bubble sort, insertion sort, etc. All these algorithms have their own pros and cons. An algorithm can be thought of a procedure or a formula which is used to solve a particular problem. The question is, why do we need an analysis of algorithm? We need an algorithm analysis to know which algorithm we have to use to solve a specific problem when there exist multiple solutions to the problem. Algorithm analysis refers to the analysis of the complexity of a different algorithm and finding the most efficient algorithm to solve the problem at the hand. And BigO notation is a statistical measure we use to describe the complexity of the algorithm. Now we will take a brief review on algorithm analysis and BigO notation. But before, we had a question, which is, why is analysis of algorithm important? So to understand this, we will take help of a simple example. Suppose a manager gives a task to two of his employees, and the task is that those two employees needs to design an algorithm in Python that will calculate the factorial of a number which is entered by the user. So the two algorithms are as follows. Let us look into the algorithms developed by those employees. So the first employee create an algorithm with the name fact1 with a parameter n, and then he create a variable called product equal to 1, and then he loops over the value of n, and then he adds into the product into I plus 1. Okay, so you can notice this algorithm, it simply takes an integer as an argument. Inside the fact1 function, a variable named product is initialized to 1. A loop executes from 1 to n, and during each iteration, the value of the product is multiplied by the number being iterated by the loop. And the result is again stored in the variable called product. And finally, after the loop execution, the product variable will contain the factorial. So let us run this function and let us try to find the factorial of a number 4. And it says the value is 24, which is correct. Now let us look at the code developed by the second employee. So what he do is he create a function fact2. Inside this function, he writes a base condition which returns 1, and then he returns n into fact2 n minus 1. So you can see this is a simple recursion, right? And when I run this code and let me give a value, let's say 4, it returns the same output as the previous one. The manager has to decide which algorithm he needs to use. So to do so, he has to find the complexity of the algorithm. So one way to do so is finding the time required to execute the algorithms. So let us simply try to find what is the time taken by both of these algorithms for their final execution. So what we can do is we will use a literal called timeIt. And inside this literal, what I'll do is I will call our first function, which is fact1, and let us try to find the factorial of a number 50. Okay, so the code is executing. So here you can see my first function is taking the time of 5.15 milliseconds, right? Now let us try to find out the time taken by our second function fact2, and this time it will take again the same parameter, and let us run this code. And here you can see our another function takes the time 10.4 milliseconds, which is quite double to the first function. So now the output says the time algorithm of time complexity of the first algorithm is approximately half to the second algorithm. The execution time shows that the first algorithm is faster compared to the second one. So this example, I think, clearly shows you the importance of algorithm analysis. In the case of larger inputs, the performance difference can become more significant, right? However, the execution time is not a good metric to measure the complexity, since it depends upon the hardware more. A more objective complexity analysis for the algorithm is needed. So therefore, there comes the role of BigO notation. So BigO notation is a matrix which is used to find the algorithm complexity. Basically, BigO notation signifies the relationship between the input to the algorithm and the steps required to execute the algorithm. It is denoted by a big O followed by opening and closing parentheses. Inside these parentheses, the relationship between the input and the steps taken by the algorithm is presented using n. For instance, if there is a linear relationship between the input and the step taken by the algorithm, the big O notation used will be O of n. Similarly, the big O notation for the quadratic function is O of n power 2. You can see the following table. This shows the most common big O function. For constant, you can see this is O of c. For linear, this is O of n. For quadratic, this is O of n power 2. For cubic, the big O notation is O of n power cube. For exponential, it is O of 2 power n. For logarithmic, this will be O of log n complexity, and for the log linear, this will be O of n log n linear log n complexity. And this complexity generally increases by increasing the number of executions or the number of loops. We will take look into some of them one by one. Now let us write a simple program in Python that finds the square of the first item in the list and then prints it on the screen. And then we will just find the first element of the list item, and simply we will multiply it with the first element so that we can square it, and then we simply print. Now what we will do is we will call this function, and inside this let us pass an array. So a list could be 4, 5, 6, 7, you can say. All right. So in the above script, irrespective of the input size, the number of items in the input list items, the algorithm performs only two steps: finding the square of the first element and printing the result on the screen. Hence, the complexity remains constant, right? So this is an example of constant complexity, which is O of c, where c is the constant. Now let us look into another example. So for this time, what I'll do is I'll create another function with the name linear algo, and inside this I will again pass a list of items, and this will this time iterate through all the element in the list items, and then what I'll do, I will print each item. Now I will call this function linear algo and let us pass the variables inside it. which is, let's say we will take again 4 elements. Now let us comment down our previous code and let us run this code. So let me clear my console for clear view. And here you can see 4, 5, 6, 8 are printed sequentially. When I increase the number of elements to some more elements, let us observe output. So it will print more elements. So you can see the number of print statements are dependent on the number of items in the list. As I increase the number of items, the print is also increased. The complexity of linear algorithm function is linear. So in the above example, you can see the number of iterations for the for loop will be equal to the size of items array. So for instance, if there are 4 items which we have seen, the for loop will be executed 4 times. If I increase the number of items, you can see the iterations by the for loop also going to increase. So this is known as linear algorithm. Now let us look into another kind of complexity, to observe another kind of complexity. So for that, what we will do is we will create an example for quadratic algorithm. So for this, I will again take a list of items, and inside this I will create a for loop which iterates over every item, and inside this for loop I will create a nested for loop that will go from the same list, and then I will print these items. I will print item, and let us put some space in between them, and then I'll print item 2. All right. Now what we will do is we will simply call our function quad algo, and inside this we will again pass the same input. And to run this, let us first comment down our previous code. So here you can see the number of outputs increased. In the script above, the function which we have written, we can see that we have an outer loop that iterates through all the items in the input list, and then a nested inner loop which again iterates through all the items in the input list. The total number of steps which are performed is n cross n into n, where n is the number of items in the list. So currently we have 4 elements, so the number of steps which are performed are 4 cross 4, 4 into 4, which is 16. Where if we increase the number of elements in the item, the iterations are going to square up. If n, then it will go to n square. Now let us look into the graphical representation of all these algorithms to understand them better. So this is a graph which is representing the constant complexity of the algorithm. The complexity of an algorithm is said to be constant if the steps required to complete the execution of an algorithm remains constant. It is irrespective of the number of inputs. The constant complexity is oftenly denoted by O of C, where C is any constant number. Then the linear complexity. The complexity is said to be linear if the steps required to complete the execution of an algorithm increase or decrease linearly. Here in the graph you can see on the basis of inputs, the number of steps or the number of iterations are increasing or decreasing linearly. So this is known as linear complexity, and it is oftenly denoted using O of n, where n is the number of inputs. Now the quadratic complexity. So here you can see the graph. The complexity of an algorithm is said to be quadratic when the steps required to execute an algorithm are a quadratic function of a number of the items in the input. The quadratic complexity, we often denote it using O of n square. So in the previous example that we have seen, you can see on the basis of number of inputs, the loop runs twice, or it's just increases exponentially. So this is the reason when we have n number of inputs, the quadratic complexity goes to O of n square. Thank you for watching. For more such videos and detailed explanation, visit pythonwife.com.